All right, today we're going to be looking at the mechanical properties of ceramics, and in this first module, we're going to look a little bit at the theoretical strength and how that gets us to actual strengths. But before we do that, let's think about the situation a bit. So for ceramics, what I want you to think about is strength or is toughness more important? So the first thing to do with this question is I would definitely look up the definitions of strength and toughness. They should be in our textbook. And then figure out which one you think is more important, and then make sure you defend your answer. And then also, again, know what those terms are. So go ahead and pause the video, think about this, write your answer in the questions for today, and then come back and we will discuss. All right. So now that we're now that you've had some time to take a look at this question, hopefully today's discussion will talk a little bit more about today's and also tomorrow's lectures. We'll talk a little bit more about the difference here. But the main thing is I think a lot of people throw around these terms interchangeably, but they're actually quite different, right? Strength refers to the strength at which, or the stress value at which something happens, like failure or yielding, and so forth, right? But toughness is more to do with a resistance to fail, right? And because ceramics are fairly brittle, we're going to spend a lot of our time focusing on toughness and not so much strength. Strength is definitely a part of it, but toughness is its own thing as well. And so we're going to talk about that as we go through today's lecture. All right, so let's get to theoretical strength. So I put a table here from our textbook that gives the elastic modulus of a range of different ceramics, from oxides to halides to glasses. One quick note here is that in our textbook, for for elastic modulus, they call that Y, and you're probably used to E. So just kind of get used to that when you look through the book, that Y in this case means elastic modulus. So for the theoretical stress at which something fails, this should be, and the reason I'm putting up the elastic modulus is because this theoretical value should be the elastic modulus divided by 10. So whatever value you see here, for example, let's look at the first one. For aluminum oxide, it's 390 gigapascals. So this would tell us that if our theoretical stress level at which failure should occur is 39 gigapascals, right? And that's, again, on the order of gigapascals, not megapascals, which you're probably more familiar with. So the theoretical strength of ceramics is very high, but there's not a lot of materials that actually have this theoretical, or have strength that is close to theoretical. And that's because these flaws, right, they greatly reduce that stress that brittle materials fail. We know that our ceramics, for the most part, are brittle materials, and therefore they will fail at much lower values. So I put some comparisons here. So glass, so ordinary tensile strength of glass is only about 50 megapascals. Keep in mind that what the values were on the elastic modulus and what the theoretical strength should be. So we're on the order of 50 megapascals. That is not very high. Whereas if we have a fiber glass, so same material but in a fiber form, we can actually get a tensile strength up to 5 gigapascals, right? A big difference in 2 orders of magnitude with the strength at which this fails in tension, right? So huge orders of magnitude, and we're going to tie this back to what this has to do with the size and the amount of flaws. All right, so again, excuse me, our ceramics, along with amorphous polymers that are below their TG, act with really limited ductility. They're brittle fracture. So they act more like this left curve where we just have the elastic portion and then fracture. Whereas other materials we might be used to and from other classes, metals, ductile polymers, do have substantial plasticity, and therefore there's more of a warning when fracture occurs because it's ductile, it changes shape. So that's a big difference here in terms of the type of response we have. All right, so we know that ceramics break at lower than their theoretical values, and we know that all materials have flaws. So let's take an example of a crack-free or defect-free material. So that's the one here on the left. So this material has all its bonds intact, and then we're basically pulling it in tension, right? And so we can think of each of these bonds as a spring, is basically what this image is showing you. So the force, the tensile force that's applied here is evenly distributed across the cross section. So these three bonds, right? But in the other case, if we have a defected material, so in this case, we would call this atomically thin crack because essentially just one layer of bonds is disrupted. Excuse me. And so in this case, these three bonds are disconnected and we're left with just these two over here on this cross section. So now in this material, when we apply a force, instead of being evenly distributed across all these bonds, it's actually not evenly distributed. And in fact, what we find is that there's an intensity of that force on what we would refer to as the crack tip. So this bond right here. So an unusually high amount of stress is applied to this one particular bond right on sort of the leading edge of this crack. So that means what this is trying to show is that the stress at the tip is the highest anywhere in this material. All right, so that means that with this atomically sharp crack, then the applied stress is amplified at this crack tip. All right, so what this kind of tells us now is we know theoretically, if we try to break all the bonds in a material, it happens at a level that's roughly the elastic modulus divided by 10. So now if we extend that and have this knowledge of what an atomically thin crack does, so imagine we have a plate and we have this crack occur in it. So what's going to happen is there is going to be amplification at the tip, the leading edge of this flaw. And so when we put this under stress, it's going to be amplified at that site. And so the real condition for failure is going to be when that stress at the crack tip reaches the theoretical value. That's when we have unstable propagation of this crack, and it goes throughout the material and causes failure. And so that's why we would have failure at lower than theoretical values, because we have these flaws, we have cracks, we have pores, we have various surface flaws and everything. And when the stress value at those sites reaches that critical theoretical value, that's when it causes, and that happens overall at lower values than theoretical, because it's amplified at these tip locations. And so that's how we can get fracture to occur.